retrievals. Oh, there we go. Perfect. Fantastic. Um, yeah, so let me say that sentence again. So we're hoping to develop a data-driven, machine learning-based methane retrieval method to complement the existing matched filter-based approaches that's currently the state of the art. And we think this has a lot of benefits, and it's also an opportunity to kind of explore the space of ML data-driven retrievals and try some new techniques that could also be extended to kind of other tasks down the road. So let me get to this slide. So a little bit of background in case you're not familiar, but we've had a huge surge of imaging spectroscopy missions in the recent years. That's really bringing about a new era of greenhouse gases emissions monitoring that includes airborne and spaceborne platforms such as Tanager 1 and Emit and various European missions and MethaneSat, of course. And although there's also proposed missions as well, such as SPG Visvir and Carbonite, which is currently being competed. And so we're having this massive influx of observing platforms, and that means more and more data, right? And that also means more operationally delivered products. So Emit is currently delivering level 2B methane plume products based on this CMF retrieval that we'll talk about briefly, and very rigorous manual review. So lots of folks and lots of scientists reviewing plume detections and quantifications and such. And I have some links on the slide here for the data products and the data portal in case you're interested in using this data. So this LPDAC link has the actual CMF retrievals and the plume detections, and this data portal actually is really nice for just kind of scrolling around on a map and finding all the plumes that have been detected that have been delivered to this portal. So I encourage you to take a look at that if you haven't already. So a little bit of background on the retrieval itself. So as you probably know, the methane absorption signature is mostly in the viswir, which makes imaging spectroscopy an ideal method for detecting them and retrieving them. And for that, the primary method is this column-wise match filter and its many variants, right? There's a lot of modifications that have been made over the years. But overall, still, the column-wise match filter is the most well-validated and well-characterized methodology. Thoroughly described in these two papers that I've cited here, but on the right, essentially, you're taking the covariance of the background and determining if this current pixel has an absorption compared to the background, right? Um, there's a lot of active research still going on with this retrieval method, so, especially in our team as well. So, couple shout outs for some very recent manuscripts I wanted to share. On the left, we have Jay Follin's work that actually creates a sensitivity and uncertainty product for the column-wise match filter, which is very useful because, as we know, this column-wise match filter retrieval is very sensitive to surface albedo, and like if your plume is crossing over a water body or something like that, like it's not going to retrieve much, right? So it's great to be able to quantify that and to actually correct the CMF retrieval based on surface effects and uncertainties and sensitivities. So that's some recent work in TGRS from last year. And then on the right, this manuscript's still in review, but a preprint is available. This is from Shushu's work, also in our group, where we can actually post hoc look at some of our plume detections, look at the spectra, and determine if this is an actual methane observation or if it's some kind of confuser or some kind of similar material that's mimicking the methane signature in the visware like absorption bands. And this is actually fantastic because it's very difficult to tell by eye on whether something is a true methane retrieval or if it's a false positive. And this actually segues really nicely into my next slide, which is that whereas the CMF is really efficient, well characterized, well validated, it still has its limitations, right? So it's mostly plagued by these quote unquote false enhancements, which is where we have false positive detections due to kind of various factors. One such factor is confuser materials, right? So if you look on the left, sorry, on the right, this middle plot, that's some observation where it kind of follows that dip in the Visware, the methane absorption pattern, but it doesn't actually, right? It doesn't have the little fingerprints necessary, but in the CMF, because it's just taking the Euclidean distance, it can't actually tell that. So if it just follows the path of the absorption, it just kind of thinks that it could be methane. We also kind of commonly have issues with high albedo surfaces, so very bright surfaces oftentimes light up as methane retrievals. And anytime you have some kind of a very bright flare in the column, that contaminates the background covariance. So just to say that again, right, because the CMF relies on statistics about the background, in our case, the column, right, it takes the average and it takes the covariance matrix. If you have any kind of spectrum in that background that's very bright, like a flare, where it's actually emitting photons and not just reflecting, then it actually completely messes up your background statistics and it ruins your retrieval for that entire column. So a lot of work actually has gone in operationally to mask out those flares or correct those background covariances. So all of these kind of factors, and actually you can see a lot of those examples on that bottom plot there, results in false positive source detections. So for this plume detection task that a lot of us are doing, where we're trying to detect these plumes automatically, these false positive detections ruins a lot of our detections because sometimes they look like plumes, right? And also for quantification, right? If you have a true plume that's crossing over one of these kind of false positive um, enhancements, that also inflates your plume quantification as well. So that's kind of rush job at explaining the background state of the field. But kind of in summary, there's a lot more of these observing platforms going up to detect these greenhouse gases emissions. But the current state-of-the-art algorithm we have right now has a few points where they could be improved. So to kind of help alleviate some of these issues and to kind of complement this current state-of-the-art CMF method, we're hoping that a pixelized deep learning retrieval could accomplish a few different things. So the main thing that at least I came at this with is that we want to really avoid these artifacts, these false positive retrievals that's caused by these column-wise characteristics, because now you're just doing retrieving pixel by pixel and not relying on the background statistics. And we also think that a deep learning method could model these absorption features better for these trace gases. So instead of just looking at a Euclidean distance between an absorption and an observation, perhaps actually looking at the shape of the spectra and making a determination there. We also think that a pixel-wise retrieval would decouple retrieval quality from observation track length, and this means that oftentimes these instruments, especially in airborne cases, you have to fly these instruments for a long enough distance to get enough of a background statistic to do the retrieval. But if you just do it pixel-wise, you don't have to do that. And then finally, we're always trying to improve the downstream tasks. So detection, quantification, and all these other things we're interested in doing with this retrieval product, we hope that we can improve the accuracy. So to do that, we're proposing this interpretable and pixel-wise deep learning retrieval that also has uncertainty quantification. And shout out to William's work at the bottom here, where he did this kind of uncertainty work for OCO2 and XCO2 ML retrieval. Um, Yeah, great. I realize we still have a lot to get to, and unfortunately, I spent too much time on the background, so I'll keep moving here. But yeah, we're trying to leave enough time at the end for questions. So please, leave them in the chat or write them down, and we'll make sure we address all of your questions at the end of the presentation. So our approach is pretty simple here. So we're first going to produced a synthetic data set of injected CO4 and CO4, CH4, CH4 into background spectra. So every data-driven task is you need a strong data set in its foundation. So we're going to spend a lot of time curating this data set of injected methane. And then we're going to train this spectroscopic transformer, which I'll briefly talk about. And then on top of that, we're going to have the model predict uncertainties for both the data and the model with this method called deep evidential regression. And then finally, we're going to evaluate some results and look at the retrievals and not in this presentation, but eventually validate the downstream tasks. So I'm going to hand it off to Will here to chat about our data set.
Thanks, Jake. So I know you guys had Max Reuter on the pod a few months ago, I believe, with his CO2M neural network based retrieval. I've worked a bit with the OCO2 team on this. In both those missions, we have access to essentially the forward model to produce radiances, any radiance in the instrument range for any desired atmospheric state. In the case of emit, we're actually just going to take advantage of the really large catalog of background observations or pixels. Showing the distributions here, we split. We do an initial training test split just by scene ID or FID, if you're familiar with the emit database, and we take the full range of the catalog. And if you'll go to the next slide, Jake. And so in the cases of CO2M or OCO2, where we have this OSSI environment, this simulator environment, we need to take these, in our case, we need to take these background pixels and inject some methane signal into them. We do this with a kind of a simplified RT equation derived by Phil Broderick and David Thompson. And the first step is to resolve for the surface radiance using here we call L background, that's our observed radiance. We also resolve for the path by interpolating into a lookup table that's produced by a radiative transfer model. When we interpolate in, we have some previously retrieved atmospheric values like water vapor, plus our viewing geometries. And we hard set a CH4 value at a background range. Once we resolve for the surface, we can then choose another elevated CH4 label, which we'll also set aside as the training label for the machine learning retrieval. And we will reinterpolate in using that elevated value and calculate the injected radiance. In this method, if anyone saw our AGU presentations, we were using a slightly different injection method that was allowing our retrieval to see methane, but only very close to the surface. This particular method, using the simplified RT calculation, allows us to capture some of the nonlinear interactions that happen in the absorption range for much higher ppm concentration values. And I'll pass it back to Jake.
Yeah, thanks, Will. Just to briefly mention, we're ensuring that we sample pixels that don't have methane in them by only using scenes that don't have observed methane plumes. So we're kind of making the assumption that when we're doing this massive sampling of millions of pixels, that most of them have a negligible amount of kind of methane trace gas, or at least compared to the instrument sensitivity limitations. Okay, I'm going to briefly go over this. I'm not going to belabor this point too much because we do have an article in press and a preprint that's available. But this model is called a spectroscopic transformer, and it's a deep learning architecture that's specifically kind of intended for imaging spectroscopy and specifically like pixel-wise application of this model, right? And so just to kind of briefly describe this model for those interested, we're essentially treating the each observed spectrum as a sequence, right? And we're just feeding it through a very simple transformer encoder module here. So you represent this 285 length spectrum as a sequence of wavelengths and reflectances. And then we're hoping, and we're demonstrating actually, that this attention mechanism is learning some physically meaningful properties about absorption features in the spectrum. And so we think this is more robust than just training a model that thinks each wavelength is independent, because it's not, right? This model hopefully understands that wavelengths that are nearby are correlated and that wavelengths far away are still related, and kind of learning all of that from the data itself. And the big kind of benefit of this transformer model that is that this architecture is inherently interpretable. So it actually generates these attention scores that we can look at and actually identify which parts of the spectrum the model is looking at to make its decisions, which is really interesting. And this preprint is demonstrating this architecture on a new EMET cloud mask product that we're all very excited about because it is a massive improvement in the cloud mask, and we're going to deliver that as a L2A mask product. But now we're hoping to extend this to the methane retrieval task. Um, so that's our backbone kind of model architecture. And back to Will to talk about the uncertainty quantification.
Sure. So ideally, in addition to an improved point estimate, we hope to have a really robust uncertainty of that estimate as well. That ideally correlates with identifying any remaining false enhancements in the scene, particularly surfaces that maybe weren't included in the training data set or atmospheres that we didn't observe in the training data set. So one means of doing this that's kind of the state-of-the-art benchmark is deep ensembling, where you essentially train an ensemble of neural networks. Usually you need to encourage some sort of diversity in that ensembling. So there's a whole bunch of literature about random weight initialization and different methods to ensure that diversity. Sometimes this is done just to capture what we call that epistemic uncertainty by training just an MSE loss, standard MSE loss regressors. But we're also interested in capturing the data variability or the aleatoric uncertainty. The epistemic uncertainty is the million-dollar word if you're not familiar with the UQ background of basically being a good indicator of things that are out of distribution. So we clean up our training data set a lot, not to include water pixels, not to include flares. So we're hoping that something like that will flash hot in the epistemic uncertainty. And then the aleatoric uncertainty is essentially regions where in the data where we might trust the model's prediction, but we just need to be aware that the posterior is quite wide there. Ensembles do a great job of capturing both of these sources when you train with a Gaussian negative log loss. Essentially, you have two outputs from your model, the point estimate and the estimation of variance. And if you look at this toy example down here, the purple or blue is much, that prediction interval is much wider. It takes over in ranges where we're lacking training data. So those little red dots are the test data set. The training data exists from -2 to 2. We have out of distribution data from -3 to 3. We have a region in the middle with high data variability, and we can see the aleatoric component really dominates there. And then the epistemic component dominates once we get to that out of distribution region. And we can go to the next slide. So there are some drawbacks with ensemble methods. You have to train a lot of models, so that can slow you down at training time, and of course it can slow you down at inference time. So we're aiming to try and do this, capture both sources of uncertainty. We want really robust epistemic and aleatoric, and try and do it with a single model. This paper by Amini et al. Called Deep Evidential Regression proposes a way to do just that. Rather than just model that mu and variance, that point estimate and variance, we're going to define an evidential prior over those, where the point estimate is drawn from a normal, and the variance is drawn from a inverse gamma distribution that are parameterized by these four outputs from our model. So our model is going to output these four, what we call the evidential prior parameters, a gamma, a nu, an alpha, and a beta. If you're familiar with like hierarchical Bayesian methods, that's exactly what's going on here. So we form our posterior is no longer Gaussian. It takes on a new form. With our evidential prior, we have a conjugate distribution called the normal inverse gamma, and it's given as such here. It's quite a monstrosity. Next slide. So in so many words, evidential methods essentially treat learning as an evidence acquisition process, where if we have sufficient training data and our model is performing well over that data, we want to increase the amount of evidence in that region or that region of the training domain. If we are in a region of the domain where we're performing poorly, perhaps due to sparsity of data or outliers, we want to penalize that evidence and reduce the evidence over that region of the training domain. Formally, this is defined as conditional of an observation y sub I given our evidential parameters by marginalizing over the lower order distribution parameters mu and sigma squared. Anytime you have these sort of Bayesian methods, you run into all sorts of issues with trying to do calculations over a pretty intractable integral. But thankfully, since we were really smart about our choice of prior here, and we have this nice conjugate, we have a analytical solution for this. After quite a bit of algebra, you can go back to that Gaussian negative log loss and plug in the conjugate distribution, and you get a pretty long loss derivation here. Plus, we also add this regularization term at the end where a lot of the magic happens. Essentially, if we have incorrect evidence where we have poor prediction performance, we penalize that heavily, also tuned by this lambda hyperparameter, which essentially controls, it can be thought of as just inflating or reducing the epistemic portion of the uncertainty. So we can go to the next slide. And so what's going again, just to TLDR, the deep evidential regression, we have 4 model outputs. We have this modified negative log loss. Our point prediction is just that gamma value, that first parameter. And then the aleatoric uncertainty is just given as beta over alpha minus 1. And the epistemic uncertainty component is just given as the nu being included in the denominator. And you can see on the right 2 examples of tuning this lambda. This is pretty problem dependent. So you do need to do a sweep through this parameter. And you can see how it inflates and deflates the epistemic region for the same toy data set. And I think I'll give it back to you, Jake.
Yeah, thanks, Will. When I first learned about this, it kind of sounded like magic. So we're happy to chat more about this kind of after the presentation. But we're really excited because we can demonstrate that this actually gives us an equivalent, if not better, uncertainty quantification than the ensemble method that Will showed as a baseline at the beginning. Okay, so we'll show some results finally. I'm sure that was a lot of content. This is the kind of base thing that you want to see, which is a scatter plot showing the true injected methane on the x-axis and the predicted methane on the y-axis. So on the left, you have the training set, and on the right, we have a test set. And I should mention that this is with a pretty small model, maybe 50 or 60,000 model parameters, which is tiny for deep learning. But that's mainly a consequence of, first of all, our architecture, and second, we haven't gotten around to training bigger models yet. So we're hoping that these numbers will kind of improve as we increase the model complexity and such. But these are preliminary results, just kind of showing proof of concept for this approach. So on the left and on the right, they both follow the one-to-one line. We start seeing a little bit of underestimation as we get near the higher concentrations. We're wondering whether that's a model artifact or if that has to do with the actual nonlinearity of the injection itself, whether it's just not capturing that. We're still diagnosing. But overall, we're pretty confident that the model is able to retrieve the signal, at least from these injected pixels, which is not a given. Like this was, we weren't sure that that the model would be able to even retrieve this amount of injection, but it's doing great here. Okay, some actual rasters. So on the left, we have a plume complex retrieved by the column-wise match filter. This color bar is going from 0 to 1500 ppm. And on the right, we have this retrieval from our evidential spectroscopic transformer. So a couple things I want to point out here. So we've retained all of the plumes that are detected in this retrieval. And the main thing we were excited about when we saw this was that this road, right? So these ground infrastructure features is what often gets highlighted in these CMF retrievals, and it's completely disappeared or mostly disappeared. I'll give you that in our in our deep learning retrieval product. So this is exactly what we're looking for. We're looking for a reduction in the background enhancement, right? So the background noise levels have decreased a little bit, and we're also rejecting these kind of confuser materials. I will point out that on the left, compared to the left on the right, you start seeing these kind of streaks again, these column-wise streaks. And that's mainly because, again, we're not normalizing per column anymore, right? We're not using the background statistics per column anymore. So if there are calibration or kind of noise characteristic differences between detectors per column, then that's going to start to get highlighted a lot more compared to a column-wise method. So that's kind of what you're seeing here. But otherwise, if every retrieval looks like this, we're very happy, right? This is exactly the kind of behavior that we're looking for. On this top left corner, this is actually a water body that we identified, I think, or it's a cloud. It's one of the two, but it's out of domain, and we're going to demonstrate some of our uncertainty quantification features with these kind of LOD pixels. Just to show you these plumes a little bit closer, so you can see kind of the details from these retrievals. This is a flare dropout, or it's some other dropout due to the background covariance being contaminated. And again, we avoid that by using a pixelized method. And on the right is a kind of a Viridis color map of the uncertainty quantification. And it looks kind of blank. And the reason for that is that there's this dominating signal on the top right here. So we can actually take a look at that a little bit more closely. So this is that here, sorry. This is this top right section of the retrieval that I'm highlighting here. And if you look closely here on the left side, there's a lot, so I'm going to break this down. But on the left, we have this plume that's been retrieved as 10,000 ppmm, which is way outside our training set. So something's going on there already. But it has a bit of a lower uncertainty. It has a 600 ppmm uncertainty, and at least the plume, the spectrum at least looks reasonable, but it is an out of bounds prediction. So it's going to have a higher uncertainty compared to these other pixels on the left here, which sit more around 2000, 3000 ppmm, and therefore have a much lower uncertainty. So this is this epistemic component that Will's been talking about, where if the model's predicting something that's kind of out of bounds or out of distribution, it's going to elevate that uncertainty. The more exciting thing here in this example is on the right, because this pixel has been predicted as 10,000 ppmm, but also the uncertainty is 46,000 ppmm, right? So it's the model's really blowing up there. And if you plot the spectrum, this is a flare. And this is actually a flare that the emit flare mask wasn't able to catch because it's a very weak flare, but a flare nonetheless. So it's actually emitting photons and such. So this uncertainty products is actually helping us catch this kind of phenomena, and it kind of leads towards a possibility of perhaps masking these retrievals based on some uncertainty cutoff or something like that, right? But again, it's pretty exciting that this uncertainty is working to kind of catch these edge cases of out of domain, out of distribution data samples. The other thing I'll point out is that this bottom plot is also showing the attention score in addition to the spectrum. So this color bar is the attention score that the model is outputting as an interpretability product. And we see that it is lighting up around the methane viswir absorption region, right? But it's also looking at some other features throughout the rest of the spectrum. So that's kind of interesting to see where the model is looking. And it's mostly ignoring 450 to 1300 for good reason. But in the near infrared and the visible region, it's paying a lot more attention, literally. One more example here, just to kind of show, I guess we could describe this as a failure case, but it's really more of an out of distribution case. The plume in this case is on the left, just below this dropout row here. You can still see it in the spectral the evidential spectral, oh my gosh, the deep learning retrieval. But what's probably drawing more of your attention is this crazy region on this right, this bright re red region, as well as this region over here. And that's because, again, we didn't train the model on any water body pixels, nor did we train it on any like infrastructure pixels, right, of like bright roofs and such. So the model is going to kind of predict whatever on these regions. In this case, it's predicting very high. But on the right, you can see that this uncertainty is also completely lighting up. And it's saying, hey, I'm predicting something because the model has to predict something, but I'm warning you, my uncertainty is higher than the actual prediction is. So like I haven't ever seen this before in my training data set, and I'm going to tell you that, which is very, very, very useful coming from a deep learning model. And actually, again, we can kind of go into these pixels and look at the spectra and try and figure out what's going on here. And so on the left, this is pixel is an actual methane retrieval. There actually is methane there. And by the way, it's a good thing that the uncertainty doesn't track with the plume. You really wouldn't want to see the uncertainty, the plume and the uncertainty raster, but it is showing kind of surface features, which is great because the uncertainty of the sensitivity of the instrument relies on the brightness of, and the reflectance of the surface. So it makes sense that the uncertainty correlates with the surface features here. But again, we can kind of look at it. This color map isn't scaled very well, but again, it's kind of the most highlighted region is this visual absorption region. But as we kind of get over to, I think these are solar panels or some kind of ground infrastructure where there's, it's reflecting a lot that the model is lighting up on. But again, it's predicting 4,000 ppm with an uncertainty of 2,500 ppm. So in any normal case, you would throw out this retrieval. But again, we can try and look at this attention map and see where it's paying attention to. And there's this spike at around 1750 that it's looking at here, and around 1600 as well. So it's, and by the way, this attention isn't just for the actual retrieval, but also for the uncertainty. So where is the model looking at in the spectra to determine the uncertainty, not just the actual retrieval. And we can kind of investigate that. Maybe that informs our next round of model training, data set curation, etc. Yeah, Will, do you want to talk about this slide real quick?
Sure. So these are called ECE plots. These are essentially great eyeball checks for how good your uncertainty is doing. So across the x-axis, the best way to explain these is we take a z-score across percentiles. We bin our prediction interval for each percentile multiplied by the z-score. And say for a one standard deviation, you'd expect to see about 64% of the ground truth in the coverage of your prediction interval. Across each z-score bin, if we're perfectly within the theoretical coverage, we would say our uncertainty is perfectly calibrated. We'd be right along the one-to-one line. Of course, there's a little variability there. So we see in these plots, we're doing pretty good. We're pretty close. And on the left is an ensemble, the negative log likelihood loss ensemble with 5 members. This is kind of the standard to beat. And we see that our single model, our SpecTF evidential model is doing quite good, if not better, in the overall uncertainty coverage.
Yeah, thanks, Will. Yeah, so it's great to show both kind of empirically just by looking at examples, but also quantitatively that we're doing a good job of really quantifying this uncertainty for our retrievals. Especially compared to something like an ensemble model, right? Like that keeps us from training 4 more models, if you will, and inferencing with 4 more models really speeds up our compute time. Okay, yeah. So again, this is really ongoing work. A lot of these results were generated like 2 or 3 days ago by Will and I, right? This is active work. So we're interested from hearing from you all as well as any questions or suggestions that you might have with this approach. Ourselves, at least right now, we're trying for even larger, even more diverse training data set. We're training on about 3 million pixels right now, but a lot of this work relies on that diversity and the coverage of that training data set. So we're trying to go for, 10 million or more even. And a larger capacity model, we just trained another model yesterday that's twice as large as our current model, and we can already show that it's doing significantly better in terms of the negative log likelihood loss. So we're interested in running that and seeing what that looks like. There's some hyperparameter tuning to do. Right now, we're not really getting the balance of epistemic and aleatoric uncertainty that we'd want, but the combination still works very well. So we're still kind of dealing with that. And of course, much, much more validation to come with the taking advantage of the emit plume catalog as well as validating downstream tasks like, does this improve quantification? Does this improve detection? It'd be really cool to demonstrate this with some kind of controlled release experiment, but we have way longer to go before we're there. So yeah, thank you again for inviting us and for letting us kind of share our work here. Again, I'm happy to answer any questions that you might have going back to the earlier slides or talk about anything else. So thank you again. Appreciate it.